to the model and to the hypothesis that we're actually working with. So let's put this situation and the challenge and the question we'd like to answer into the statistical framework that we are getting used to now in this course. Here is the model that expresses the situation. And by model we mean the definition of all the assumptions and the statistical setting within which we are viewing the whole experiment and the data in front of us. We express the data by a double index here. I for the group, so that would be 1, 2, 3, or in the TV picture thing 1 up to 12, because there were 12 groups of data there. And then J for the individual observation within each group. So we have a double index notation. We have an overall mean. We have a deviation from each group, deviation from the mean for each group. So they could have each their individual mean. We could also have called this alternatively just having a mu I, which would then sort of be mu plus alpha I. It's a bit of tedious double notation, but still this is how the work looks, so I'm sharing it with you, and there is a reason. So there are 3 different means in play. That's not so complicated a model. A few weeks ago we saw the 2-sample model. That was a 2-mean model. Now I have a 3-mean model in the outset, or a 12-mean or whatever. And then the variability within each group, that's what we say here. So the deviations from the individual group means are normally distributed observations or errors or residuals, and they are assumed like the regression models. There is a non-trivial assumption here that the variability is the same in all of the groups. They are not allowed to depend on the groups in this model. They are assumed to be homogeneous. Exactly the same kind of assumption as we do in linear regression type models and the standard models. So the hypothesis that we are wanting to investigate, I claim, is the overall hypothesis of all of the means being the same. And with this sort of indirect way of expressing it, all of these alphas, all of the deviances from the overall mean is assumed to be 0 in the null hypothesis. That's the hypothesis we'd like to design a test to tell us about. Are the means really different here, or are they not different? That's the question we are going to answer. So the alternative is that, well, some difference occurs somewhere. It's not very specific, but just something is there, some signal somewhere. So it can be a quite, vague hypothesis to test, actually, if you have many products. But then we have some post hoc thing coming up that can help us in those cases. That's what we will do. That's basically the model and hypothesis. It's, I hope, not extremely complicated. It's just the 3-group version of the 2 independent sample situation that we met some weeks ago back in chapter 3. Now I have 3 independent groups with the same sigma, different means. So 3 different normal distributions, you could also say, with each their mean. That's the basic setting that should be fulfilled, and we'll check the normality at the end of it. And then we could check it within each group, but now we'll do the residual checking like in the regression models and pool it all together. When we check normality, that's slightly more powerful. That was model and hypothesis. Let's see if you listened in. Most of you listened in. Analysis of variance, the model that I just showed you. Funny enough, if you forgot, most of the interesting thing of the analysis of variance model is that the model expresses that the means are different. So still, that sounds a bit odd as a funny name for a model and a situation that focuses on investigating means. Still, we name it analysis of variance, which, if you just listen to those words, it really seems as if the purpose of this analysis would be to focus on the variances. Well, it's actually not. Maybe indirectly so, but specifically so, actually not. Analysis of variance is for investigating means and differences of means. Good to have you. That's just per nemt, not a big problem.